Okay, so today's lecture is about discrete time control. Discrete time control will have three main parts. This is the first part, discretization. So, first of all, I would like to mention that unlike continuous time control methods, when you have a discrete time control algorithm, you can directly execute it in embedded code when you implement the software. For example, if you look at one of the control algorithms, output feedback control algorithms that I cover for continuous time, right, you have control signal depending on the control gain k multiplied by x hat estimate of the state. And this is the Lomberger observer x hat dot equals to its right hand side. So I am just showing this as a candidate control method to give you an idea. When you implement this in discrete time, so since you have x hat dot here, you need to discretize it. But once you do that, this process for, when you are basically implementing a continuous time control method, since you need to do a discretization, this can result in loss of stability margins. From that standpoint, it may be more advantageous when you directly work with a discrete time control method. In this case, again, I am going to use this as a candidate. I am going to talk about control methods, state and output feedback in this discrete time series. This is the discrete time equivalent version of the continuous time method, uk equals to minus kx hat. K is the time instant. It can be 0, 1, 2, 3, 4. It goes as k goes to infinity, similar to time goes to infinity. Basically, in this case, you have the next iteration of x hat will be the right hand side. So instead of having dots, we have this next iteration will depend on the previous iteration like this. And since during these videos, it may be not the best idea to use this k plus 1 and k, I will simplify the notation. For example, instead of using x hat k plus 1, I am going to use x hat plus to denote the next iteration of the x hat. So, and for x hat, so the signals that depends on k, I will just drop the k. So instead of using this, I will use this equivalent notation, and I just wanted to mention upfront. All right, so first of all, you deal with, most of the time, continuous time physical systems. Well, of course, there are some systems that you can capture the motion by hybrid nature, which has continuous and discrete together. But more generally, we deal with continuous time physical systems most of the time. But let's say our system is linear. It doesn't have to be. X hat dot equals to ax plus bu, y equals to cx. You get output y of t. And then when you would like to, measure this signal and take it inside the microprocessor or computer, you sample it. And this delta is the constant sampling time. So basically you sample periodically, so that if you look at this continuous time output, you get each delta seconds. This is the first sample, second sample, third sample. Basically, periodically you get samples of this signal. So this y of k looking like this as compared to y of t that looks like this. Then this comes to your control algorithm. Again, this is the candidate discrete time control algorithm. We are going to cover other stuff as well. And basically, it uses this y of k, here y of k, and it produces a control signal for each time instant like this, at each constant sampling time delta. Then basically, before we inject this to the actual continuous time physical system, we have u of t. We use a zero order halt operator that converts that signal to this form. Basically, it takes this value here, it holds it constant over the delta seconds, then it takes the second dot here, it holds it constant, and it goes like this. So this is the signal that goes to control your continuous time physical system. All right, so since we are interested in developing discrete time control methods, the first step that you should do, very first step, is to discretize the continuous time physical system. In this regard, you have two methods. Actually, I apologize. You have approximation-based methods and exact discretization methods. Approximation-based methods can be first order, forward Euler, backward Euler, Runge-Kutta, so on and so forth. We can make this list longer. And also the exact discretization. I only talk about one of the popular approximation-based methods, so-called first order Euler method, which approximates x dot as x plus the next time instead of x minus x divided by delta. This is forward Euler method. If this is x minus the previous version of x, let's say x minus divided by delta, sampling time, this is the backward Euler method. So when you have a linear system and you use this approximation for the x dot, basically I'm taking this, putting it here, then we arrive to this difference equation. So basically x plus minus x over delta equals to ax plus bu, or you arrive x plus equals to x plus delta in parentheses ax plus bu. Now let's group terms that depends on x. You have, since you have identity here, identity plus delta multiplied by A. This is your AD matrix, discretized A matrix. And this is your delta multiplied by B is the discretized, basically, B matrix. So this is your discrete time equivalent of your continuous time system, which is an approximation. Exact discretization is basically an approach. You take x dot like this, a linear system. You calculate AD as matrix exponential e to the power of A at a desired sampling time, delta, or step size, and BD as taking the integral from 0 to delta, again, matrix exponential A, delta minus S, BDS, and then once you calculate this AD and BD, you put it here, you have your discretized linear system. Now, I showed the derivation of the first order Euler method, not the exact discretization. This derivation is a little bit involved. I wouldn't say it is difficult, but a little bit involved. If you want a reference, how we arrive from here to here, why we have these AD and BD forms, you can send an email or leave a comment. I would be happy to provide a reference on that. Now, if your system is nonlinear, you can do two things. First thing, if you go to this video, you can linearize your nonlinear system at a desired equilibrium point and obtain the continuous time version, and then use either first order Euler method or exact discretization for the resulting A and B matrices to obtain discrete time version of that continuous system at this desired equilibrium point. Or if you want to directly discretize a nonlinear plant, this exact discretization won't work, but you can apply the same steps using first order Euler method. I would say if your system is highly nonlinear, which is not the topic of this part of the series, I wouldn't go with first order Euler method like Runge-Kutta type of more advanced discretization methods for nonlinear systems will give you more accurate discretizations. Anyway, as this point said, let's compare an approximation-based method, which is the first order Euler method, since it is popular, with the exact discretization. I am taking this continuous time system, x that equals to this A matrix X plus B matrix U. This is the output. First, I will work with first order Euler method. It is simple. From the previous slide, AD is identity plus delta A. I am choosing delta to be 1 second, the step size, and we obtain this AD matrix. BD is delta multiplied by B, since delta is 1 and we have the same B matrix. So the resulting discrete time system will be X plus AD, this AD for the first order Euler method, BD, this BD. Output remains the same, 1, 0, X, because, right, so your output doesn't require discretization. It is correct as it is. Now, exact discretization involves the computation of this matrix exponential, also called as the state transition matrix. There are several ways to compute the state transition matrix. If you're interested about this, let me know. I would love to provide videos about that. I simply use Wolfram Alpha, a reliable source. Basically, AXPM command, this is the not AXP, but AXPM command. I included M here. This is the matrix exponential. You can directly type this by pressing this mat input. And you insert this matrix A multiplied by 1. 1 is delta. So this is basically, I wrote this side. Then I clicked here. It produced me this 2 by 2 matrix, which bunch of cosine and sine terms. Note that these are constants, some constants, like Euler number, square root of 3 sine. So once you basically type them up, you are going to get this AD matrix here or here. 0.66, 0.53, minus 0.53, and 0.13. Now here, I am also computing the BD matrix for the exact discretization method, taking the integral from 0 to delta. Delta is 1. Again, matrix exponential. A, 1 minus S, which stands for delta minus S. Delta is 1. B matrix and DS. You click here. And you get this result. Again, if you plug numbers here, you are going to get 0.34, 0.53. So now, with the exact discretization, we arrive to the discretized system, with AD matrix being this one, this case, for the exact discretization, and PD is this. Now, I would like to compare the differences between first order Euler method, which is an approximation-based method, with the exact discretization here. First of all, I would like to jump here, exact discretization. So delta is 1 second, step size is actually quite large. We usually use we usually go up to 0.001 or 0.005 when we implement control signals. Also, as is being said, some cheaper systems, microprocessors can require 0.1, 0.2 seconds, but 1 second is quite large unless you are dealing with process control type of applications. But regardless of the step size, if you choose delta equals to 1 second, that we choose here, if you choose 2, 3, 4, the key of this exact discretization, or why we call it exact discretization, basically look at this continuous red curve. This is the continuous solution for state 1, and here x2 is the continuous solution for x2. At each delta seconds, 1 second, 2 second, 3 second, your approximation touches to your actual continuous time solution, which is very important. So at each delta seconds, x of t equals to xk. For this reason, when I deal with continuous time, when I discretize continuous time, linear time invariant systems, this exact discretization method is my personal favorite. Which worked great for numerous applications for me. All right, so first order Euler method is not that bad, but there is a big but. If delta is 1, you'll see here, this is the same continuous solution. You deviate a lot when delta is 1. If you go back to here and repeat this process when delta is 0.5 seconds or 0.25 seconds, you have these blue lines when basically delta is 0.5. If you reduce it further, delta is 0.25, you get these green curves. As you see, as delta goes to 0, you can recover continuous time performance, but as I said, you may need a powerful processor for this. Even if you have a powerful processor, I would say that why don't you use exact discretization and more frequently hit the actual continuous time solution at more frequently at each delta seconds. Again, for this reason, I would strongly suggest exact discretization if you are dealing with linear time invariant systems, as compared to any approximation-based methods. And again, I just showed first order Euler method as one of the candidates. All right, thanks.